Okay, so activity also is equal to K times N, where N is the number of radioactive atoms that are present. So we can say that the decay constant times the number of atoms is going to give us the activity. And we also can measure something that's called specific activity, where we want to know that per unit weight. So let's see, there's an example in here where, let me see what they're doing here. What's the mass of 1 microcurie of cesium-137? I found this particularly interesting because I have a Geiger counter that actually has a calibration. It has a calibration mass of cesium-137 that is, or at least it was when it was originally put onto the Geiger counter, was 1 microcurie. It's probably down to something less than a half of a microcurie now, because I know that this Geiger counter is, I probably got this about 30 years ago, and that's about the half-life of cesium-137. So probably half of that stuff is gone right now. But you know, it would have decayed to a stable isotope in the interim. But anyway, we can take 1 microcurie. This is on page, I'm on page 21 right now, and we can use that that number. You know, again, going from microcuries to decays per minute, we know that there's 2.22 times 10 to the 6 decays per minute per microcurie. So we know that the number of decays is going to be 2.22 times 10 to the 6 decays per minute, since we have exactly 1 microcurie. And then we can use this relationship, A equals K times N, where N is equal to A divided by K, which is equal to A times the half-life divided by ln of 2. And if we actually substitute into that equation, we'll find out, we're going to run into a little bit of a problem here. The book points this out, because we're going to be multiplying 2.22 times 10 to the 6 decays per minute times the half-life of cesium-137, which is 30.07 years. Now, in 30.07 years, we can't multiply years, we can't have years on the top, and then minutes, then decays per minute, because minute does not go into year. We want these things to actually cancel out. So what we have to do is either convert, we can find the number of minutes in a year and then convert that times, you know, multiply that by 30.07. And that's what's actually being done in the next part of the problem, where it says n equals 2.22 times 10 to the 6 decays per minute times 30.07 A, which is for annum, for years, times 5.256 times 10 to the 5th, that's 525,600 minutes in a year. That then is converting years into minutes. Then this whole thing will cancel out, and then you're going to find out that that's going to be equal to 5.06 times 10 to the 13 atoms. And we can convert the number of atoms into grams. Once we find the number of atoms, we can convert that into grams. So once we have, we know that we have 5.06 times 10 to the 13th atoms of cesium. We can use Avogadro's number, which all of you should remember from your chemistry classes, that we know that there's going to be 6.022 times 10 to the 23rd atoms in 1 mole. I should have written this over further because I don't have enough room now to finish my calculation. So let me just redo that again. So we had 5.06 times 10, 5.06 times 10 to the 13th atoms. And I put that over 1 just so you can see this is the numerator and that's the denominator. And we're going to multiply that by 6.022 times 10 to the 23rd atoms per 1 mole. Now atoms are going to cancel out, and we're going to have moles on the top. And then we can convert from moles into grams because we know that there are 137 grams. We can get a number that's a little bit better than that if we actually looked up the exact atomic mass of cesium, but we'll say this is an approximate number, times 137 grams per 1 mole of cesium. And then moles cancel out, and we're left with grams, and it comes out to be 1.15 times 10 to the minus 8th. It's a very small number, 1.15 times 10 to the minus 8th grams of cesium-137. So that's how much is actually in there. It's a tiny amount. It's that's 11.5 picograms, 11.5 billionths of a gram. But cesium is quite radioactive, and I'm glad that it is a very small amount, because I really wouldn't want to have a very large quantity of that in the vicinity of where I'm living. But I do keep that in a aerated area outside of my garage. So that's something that we can also do. We can actually calculate, we can use that information to make this kind of a calculation as well. And we can calculate how much material that we actually have. Another thing that we can do, and I mentioned this idea about specific activity. That's just the activity expressed for a particular amount of material. So we could say, in other words, when we give the activity, we say it's in so many decays per minute. We could make that decays per minute. We could change that to curies. Decays per minute could be curies, but we would do that per unit weight, as in per gram. So there's an example there to calculate the specific activity of xenon-133, and we get 1.87 times 10 to the 5th curies per gram when you do the calculations. And one other thing that you can do with these equations that I'll be giving you, or have given you already, is we can use those to actually find, and this is one of the more interesting things that you can do, since we know that we actually have a half-life in there, and we also have a time t, we can actually use that to date things. If we have all these relationships, it's possible for us to take a material that contains some known amount of a radioisotope, and perhaps if one element is decaying into another element, we may have what we call the parent element. That's the element that we started out with, which could be something like uranium-235, and this is going to decay into protactinium. So when this decays, when uranium-235 decays, it's going to decay into protactinium-231. And if we know how much uranium-235 we started out with, or if we know how, we know that from the natural abundance of uranium-235. There's certain calculations that we can make that will actually enable us to determine either the age or the half-life of the protactinium isotope, or the half-life of the uranium-235. And one really interesting thing is that in terms of artifacts that are probably 60,000 years of age or less, we can actually date these things using carbon-14 dating. Turns out that carbon-14 has a half-life of 5,715 years. So this means that, and the reason we can only go back about 60,000 years is that after 10 half-lives, the amount of radioactivity is so small that, because there isn't a lot of carbon-14 in anything, but there is a certain amount that's present. Maybe, for instance, in your body at any given time, maybe 1 out of a trillion atoms in your body might contain carbon-14. And that amount is actually pretty constant while you're alive. As soon as you die, and the reason for that is because carbon-14 is constantly being made in the atmosphere. We're getting radioactive carbon dioxide, bombardment from cosmic radiation is producing this all the time. And for living things, there's kind of a steady state concentration of carbon-14. So some of it's decaying, but you're always picking up new carbon-14 while you're alive, because you've always got this carbon exchange that's taking place between you and other living things. You're eating plants. The plants are taking in carbon dioxide. You're eating that carbon dioxide, which has a fixed, the carbon of the plant has a fixed ratio. You're eating animals that have already eaten the plants. Again, you have that same fixed ratio. So you bring that back into your body, and there's a fixed ratio of carbon dioxide in your body while you're alive. Once you die, or once anything dies, then that carbon is no longer being replenished, and it starts to decay with this particular rate. So there's a very interesting problem in here. It says, it refers to something called the Shroud of Turin. This is an interesting piece of linen, which is made from, my understanding is, I believe linen is made from cotton. And so you've got a plant, it was a living thing. And when the linen, to make this fabric, was actually made, it meant that the plant was, if it was a living, obviously it was a living plant, the plant had been killed. So you could actually date the fabric of this particular item, and you could actually find out how long ago the plants that were used to make that cotton, how long ago that was that fabric was actually. You might not know exactly when the fabric was made, because there could have been some period of time that was that lapsed between the time that the plant was actually harvested and the fabric was made. But you could at least put a range on there. You could say, well, prior to this, that this can't be any older than that, because it can't be any older than the time that the plant was actually killed. So the reason this was important, not important to us necessarily, but important to a lot of Christians, because Christians believe that this particular shroud was the burial shroud of none other than Jesus of Nazareth. So they actually wanted to establish, there was actually some studies that were done to establish what the age of the shroud was. What's interesting about the shroud is that there's an image that seems to be burned into the shroud, and it appears to be the image of a man. And if there was some computer enhancement that was done on this, and over the eyes of this this image are two coins, and the coins actually have another image on the coin, which looks like looks sort of like this. And this particular image is actually something that is found on coins of Pontius Pilate, who was the Roman procurator who, according to the Christian Gospels, was the one that actually crucified Jesus. So anyway, you've got, but it was known at that time that when people died, they would put coins over their eyes. So it's kind of interesting. You've got this image. The question was, when was this shroud? And there are millions of Christians all over the world that venerate this shroud because they believe it actually is Jesus's burial cloth. So if you actually look at the equations that are on page 23, we're using our original equation, which is ln of A2 over A1 is going to be equal to minus ln of 2 divided by the half-life times t. And then if we want to rearrange this, again, to get t, which is going to be the time, how long ago this cloth or these plants actually died, that's going to give us ln of A2 over A1 divided by minus ln of 2, which is 0.693, divided by T1 half, which is 5,715 years. And the A2 and A1, we get that from the following. What we find is that when you actually look at the shroud and count the number of disintegration, this is the actual activity, in a specific activity I showed, disintegrations per minute per gram of material, that came out to be 12.8. So A2 equals 12.8 disintegrations per minute per gram. And A1, which is what we know from studies that have been done, was we know that up until about 1950 or so, and prior to that, that the amount of carbon-14 in the atmosphere was, or the amount that was actually in organic material was 14.0 dpm per gram. So we can actually, from that, prior, this is, we know that this would have been the activity at the time when this cloth was made, and this would be the activity today. So it's fallen off somewhat. So we can use these ratios, and when we do that, we'll actually come up with a number of 740 years. And 740 years ago would have been, this is, well, I'm going to do it approximately, 740. It's actually a little bit, and these, you don't really get this kind of accuracy, but it's around 1370 CE. That's about when the cloth was made. So that clearly invalidates the Christian belief that this was the burial, well, this was might have been somebody's burial cloth, but it certainly wasn't the burial cloth of someone who reputedly lived 2,000 years ago. But whoever made it, so it was obviously done in medieval times, and if it was someone was trying to pass it off as Jesus's cloth, he did a very, very clever job of forging this. But nevertheless, we know, although there's still many Christians that still believe that this is his burial cloth, and they refuse to give up on that. They say that the few strands that were used to test this were not representative of the entire fabric. But nevertheless, nobody ever says, well, let's take the whole fabric and look at it. I mean, because they know that if we went and tested it again, we'd come up with exactly the same results. All right, a couple other things in here that you should know about. Something called branch decay. Not all isotopes decay just in one way. So for instance, if we're looking, and we were talking about cesium before, cesium has, no, not cesium, I'm sorry. Cesium actually does have a couple different decay routes, but that's not the one I want to talk about. It's copper-64, which is shown on the top of page 25. So copper-64, this particular isotope, actually has, there are 3 different ways in which it can decay. And I'm not going to talk about what these decays actually are. One of them is it can give off a beta particle. This is sometimes called negatron decay. So that's one decay route. Another decay route is it can give off something called a positron, which is a positively charged electron. So we have positron decay. This is also referred to just as beta decay. So we have beta decay, beta or negatron decay, positron decay, and the last one, abbreviated EC, stands for electron capture. And again, these are things that are going to be, that I will be talking to you about in great detail in, if it's not the next chapter, I think it's the following chapter, but not necessarily germane to talking about this idea of branch decay. It's just that there are 3 different decay routes, and we actually know for copper-64 that 39% of all the decays are coming from beta decay. So it's 39.00% from beta decay, and 17.4% from positron decay, and the remaining doesn't come out. You notice it doesn't come out to exactly 100%. So there is a little bit of a discrepancy, but we would expect it to be 43.60, but it's actually 43.57% from electron capture. Okay. So the point is, the reason we need to know about this is because when we try to do calculations based on something where there is branch decay, we're going to get answers that are not going to necessarily tell us, if we're really interested in beta decay, the disintegrations per minute that we're getting might not really represent what it is that we're actually interested in measuring. So here's an example. A sample of copper is known to contain 9.2 times 10 to the 7th atoms of copper 64. And on our detector, it's registering 2,345 counts per minute. But the detector is only able to detect beta particles. So here's the problem. Since the detector can only detect beta particles, it means we're missing electron capture and positron decay. So what we need to do is to actually look at the, and also we find out that not only that, the detector only has a 7.2% efficiency. So we want to calculate the half-life of copper 64. What we need to do is first find the number of decays per minute using the percent efficiency. So we take the 2345 number that we had and we divide that by 7.2%, and we get an efficiency, your book says, of 3.3 times 10 to the 4th decays per minute. That's on the bottom of page 25. You can see that. The actual number ought to be 3.26 times 10 to the 4th rather than 3.3, because there are actually, if you look at the data, it shouldn't say 7.2%, it should say 7.20%, and that means there should be 3 significant figures in the answer. Finally, the next thing that we have to do is to take into consideration that 39% of the decay is from beta decay, and that we can take that 3.3 times 10 to the 4th and divide that by 0.39, and that will actually give us the number of decays per minute comes out. Your book says 8.4, but it should be 8.36 times 10 to the 4th decays per minute. And then we can use that number and substituting into our half-life equation, T1 half equals ln of 2 times 9.2 times 10 to the 7th atoms, number of atoms that we have, divided by 8.4 times 10 to the 4th decays per minute, and that gives us a time of 760 minutes. We can convert that from minutes to hours, comes out to about 13 hours. However, well, I think it's actually 12.7 hours, 12.701 hours. But what this gives us is something called a partial half-life. It's not, if we want to actually know the true or total half-life, we have to then take that number and take the partial half-life number and then divide that by, in this case, if we want to find out what the I'm sorry, if we take the number that we have, which is actually that is the total. That number actually is the total half-life.